So let's start with neural networks. I'm going to think about the biological inspiration for a neural network. So when we open up a biological system and we see neurons, these are what they look like, right? And how this works is it's an electrochemical system which has a lot of different inputs coming from dendrites. So dendrites are stretched out all over the system, and they connect a single neuron to perhaps one or several thousand other neurons. And basically the inputs are coming from neurotransmitters that touch a dendrite. They're received inside, and then they're encoded as electrical signals that flow down into the cell body. And the cell itself decides whether or not it's going to fire based on all of the inputs coming from the various dendrites. And if it does fire, it's going to transmit an electrical signal down the shaft and to the terminal. And then at the terminal, it's going to push neurotransmitters, chemical responses out. And those are going to go between the gaps of the two neurons, and it'll be received again as inputs for the next cell. So when we think of this biological system, we'd like to encode some of the properties of this into our software version of a neural network, but not everything. So we don't need to mirror the fact that it's neurochemical at all. We just want to get the idea that it's aggregating information from various sources, deciding whether to transmit or not. So how we're going to do that? Well, we're going to start with the idea that we're going to have some inputs, right? These inputs come from an input layer or from another layer of the neural network. We're just going to call them X as an input. Could be from another neuron. And then each of these X's is going to be associated with a weight. Okay, we're going to call this weight theta, just like we have that before. And then each of these inputs is going to form a dendrite, just like we saw before. And we can think of each dendrite as doing a multiplication between its weight and its input. We might have many, many different weights and inputs. And when we are computing a neuron, we're basically aggregating all of these inputs and their weights together. We're going to multiply the weights times the inputs and then sum up all of the weight to form a cell body. So that's the signal that we've had in all of the linear units that we've been talking about so far: perceptron, logistic regression, as well as linear regression. We're going to also need an activation function. So this is most similar to what you've already learned in logistic regression. This just says that we're going to take the activation, which is this entire part of summing together all of the inputs and their weights. We're going to put it through another function, g. In logistic regression, we saw that we could apply the logistic function, which is basically a nonlinearity. It takes the input and then stretches it in a nonlinear way so that we can get an output. And even in perceptron learning, we saw that the sine function is a nonlinearity. And we're going to take this computed function and output it. It's going to be received as input again for a neuron higher up. And then finally, we can compute a final function that we'd like to output from our network by doing several versions of this, right? Going from one neuron to another, to another, to another, and then finally outputting it as the actual function h theta of x that we want to output. And because we have so many different weights here, we're not going to use the small theta anymore. We're going to use capital theta, which we're going to denote like this. So let's talk about the XOR function that we had problems with even in the perceptron lecture for lecture 3. We saw that we wanted to compute a function a little bit like this one over here, where we have 2 pluses and 2 minuses. These are training examples, given an x1 value and an x2 value, so 2 different inputs. And what we'd like to do is carve out the space like this. And we saw that using a single perceptron, we're not able to do that without using nonlinear transformation. So we can only draw single straight lines like the one here, okay, which is just fine if you just wanted to separate the plus from the minus here, but it won't help us in the case of the XOR. right? So what do we need to do? We can think about using several different perceptrons together. So what happens if I have this particular function h1 as implemented by a perceptron? And then in a second perceptron, I can implement this function over here, which is h2. If I had these two, I could compose them together, right? Put both of these together to form multiple perceptron system that could compute this function. And remember, the perceptron algorithm uses this function to calculate. It takes the sine of the weights times the input, and the output value is going to be +1 or -1, right? The sine of the output, right? And how am I going to do that? Well, let's take a look. We're going to build it up using several building blocks. So we're going to build it up from two blocks. We're going to build it up from an OR and from an AND. So if we think about an OR function, what is it trying to do? It's trying to compute this function whether x1 or x2 is turned on. If either of these requirements are satisfied, this neuron should fire and output a positive +1 value. If both are negative, meaning -1 and -1, then it should have a negative value. So let's go ahead and write that truth table out, right? If we have a +1 and a +1, +1, and a -1, -1, and a +1, or -1 and a -1, then the outputs are going to be plus, 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 or minus, right? Those types of values. So when we take a look at this, what's going on here? We have a bias unit. This is our x0, right? And it's always going to be set to 1. We have a weight here that we've already pre-computed for you, right? Our 1.5, this is our theta 0. Okay, and we want to make this an OR function. So how do I do that? I've got two weights here for x1 and x2, which is my theta 1 and theta 2. What should I set them to? Well, let's pretend we set these weights to 0 for a second. If we set them to 0, what happens? What we're going to get is these are going to be both turned off. Both of our inputs are going to be turned off. And I'm only going to get this +1 times 1.5. And that's going to output 1.5. That will be positive. So we've already taken care of all of these cases except just for this last one over here, this -1. It's a little bit problematic. We have to have that not fire when both of our inputs are -1 and -1. So pause this video for a second and try to figure out what values you want to put here and here. Because this is a symmetrical weight, then you can probably figure out that both of these weights are going to be identical. Okay, did you figure it out? So we're going to say that we have a -1 over here and a -1 over here. So what did you get? Well, let's see. If we put a 1 here and a 1 here, what's going to happen? Well, let's say for a second, just x1 was positive, okay? Then we're going to get 1.5 plus 1.5 minus 1, okay? What's that value? Well, that's going to be 1.5 because these two will cancel out. We'll still get a positive value. But what happens if both of them are set as -1, as we've written here? Okay, then we're going to get 1.5 minus 1 minus 1, and that will be -0.5, right? So this means that the neuron won't fire, and we've gotten it correct. What about the AND case here? Here we're computing an AND of both functions, and let's go ahead and write that out. What does the truth table for this particular value look like? Let's write it over here. I'm going to have +1, +1, +1, -1, -1, +1, and -1, -1. Here again, our output table should look like this. It should only be on when both of them are on. So we have a +1 here and -1 in all of the other 3 cases, right? All of these other 3 cases should be off. So what should we set the weights here? Again, because it's symmetrical, you can try to figure out what weights work. So pause the video for a second and try to answer it for yourself. Alright, so how did you do? Well, if I fill in a 1 and a 1 here, because my weight here is a negative 1.5, it does the right thing, right? Only when both these inputs are plus 1, I'm going to get a sum of 2 from these weights, which is going to be able to overpower my minus 1.5 here and get a true output of plus. If either of these two inputs are off, right, then I'm going to get a negative weight for one of these, which will cancel the other one out, and then I'm going to maintain my negative 1.5, and I will have an output that's negative. Okay, great. So we did the first part. Now let's think about how to create the XOR function, right? We want to create something like this from the inputs that we have. And we notice this is really just an OR function, right? We want an OR in case where H1 is on and H2 is off, or the case where H1 is off and H2 is on. If we had these two component functions, we could put them together in our standard OR and get out an XOR, the exclusive OR, right? But how could we get these? Well, we might think that these are actually a separate hypothesis that we could generate from another perceptron. For example, we might want to try to get it from a network that comes from a previous layer, right? So if we wanted to compute H1 and not H2, how could we do that from its component weights of H1 and H2? We used an OR for this final layer. Maybe we can use what we already learned and make an AND out of this. So pause this video for a second and think about what weights you could put here to get this type of output, right? If it's an AND function, you could use something similar to what we did last time and use a bias of perhaps negative 1.5. Okay, so for all of the blue edges, we're going to have a bias of negative 1.5. What value should we put for H1 and H2? Okay, now that you have that figured out, you probably are also able to figure out what the output of not H1, H2 should be. Let's also go ahead and put a bias weight of minus 0.5 for that. So we have basically here two AND gates, and here we have our OR gate. So let's see. For the blue edges that we're going into the first node, right, what are we going to put as our weights? We're going to say H1 should be on and H2 should be off. So we're going to put them as 1 and negative 1, right? So you can see what this is doing. This is going to fire and aggregate both of them as an AND. When H1 is on, that will give a positive 1 score. And when H2 is negative, this will be negative 1. It'll be times by negative 1, so it'll be a plus 1. So we're going to get a negative 0.5 plus 1 plus 1, which will be 0.5, and that will fire and contribute a plus 1 on the output, right? On the other case, if we have, for the second neuron, a H1 off and H2 on, we should have the reverse weights, right? Let's go ahead and write that. Negative 1 and 1. So in this case, we have a bias of negative 1.5, and we're going to add this negative H1, which is going to be multiplied by a negative 1 for a positive 1. So we're going to add 1, and another add 1 from H2 being on times 1, so I'll get another 1. So this is going to be, again, negative 1.5 plus 1 plus 1. And this is going to give us a positive 0.5, which is going to fire this neuron in this particular case of H1 not and H2 being on. So we've computed our XOR function. Congratulations! Here we have it all summed up nicely for you on the following slide. And this is called a multi-layer perceptron or neural network, right? We have here 3 layers because we're going to say these 3 layers are our parts of our network, right? Our layers. And we're going to call this part over here the inputs, which we're going to denote as layer 0. It's a feed-forward network because it has no particular loops. That means the inputs only feed straight forward into subsequent layers and finally arriving at a particular output here. Okay? If we were to have a recurrent network, which we'll get to when we get to deep learning, that means we would take a copy of the output and then channel it back in somewhere. Okay? We're just feeding the inputs forward all the way through the layers and arriving at a particular output. And the idea of a multi-layer perceptron or neural network is quite a powerful model because we can construct any type of surface by simply stacking together all of these different linear units on top of each other in these layers. Say we wanted to get to a model that can take our x1 and x2 inputs in the xy plane and to create a decision boundary somewhat like this one here, where we have a circle, right? We obviously can't do that with a single perceptron, but we can try to do it with several perceptrons. If we have 8 perceptrons all put together in this fashion, and ORed in a particular manner, we could construct a decision surface like this octagon here. And we can approximate this with any level of fidelity we want by just adding additional perceptrons, right? So here's a case of 16, where you can see the area surface is very small compared to the case of this 8, where you can see these green bumps here indicate places where it doesn't quite match our desired decision boundary. Because we have such a powerful model, there are 2 important problems. Do you know what our 2 problems are? Well, definitely we have this problem of being able to generalize, right? In the bias variance trade-off, we saw that when we have a more powerful model, we can drastically, in some cases, overfit and get something that generalizes very poorly, but gets very good training costs. So we have to be careful that we're generating a model that's actually fairly good to represent things that are out of sample or in our test set. We also have this problem of optimization, right? Now that we have so many different weights, each of these perceptrons has different weights. How do we set all of these values in a particular way anyways? We have to be able to train this model to find good parameter weights. We're going to see how that plays out in the next couple of lectures.